week. Any questions about processes, the creation, the termination of processes? Okay. Well, in that case, class, today we will continue with processes and hopefully we will terminate with them. What's left to talk about are two important topics. Last week we talked about the fork system call, and this week we will be talking about the second step of creating a new process, the exec system call. Now class, just because the process is created, a child process, and now you have two processes, this doesn't mean that the responsibility of the parent process ends at that point. The parent process can create one or more children processes, of course, so that it can accomplish multiprocessing, so simultaneous flows of execution. But very, very often, the parent process or parent processes are interested in how the child process terminates. Did it terminate successfully? So did it accomplish its goal? Was it stopped by a signal? Was it terminated? Etc. So we will focus in the first part of our lecture on the family of wait system calls, and we will see that there are multiple ways of finding out how a child process has terminated. So if things went all right or not. Because remember, once the child process is created, the parent is not communicating with it. The parent process has no idea what is going on in the child process. Is it executing properly? Does it have any issues? And so on. So as a responsible parent process, it is up to us to care for our children processes. Now, what does the wait system call do? System call do exactly? It receives only one parameter, just a pointer to an integer. And what it does is, when a process calls the wait system call, well, many things can happen, but what normally happens is that at that point, it blocks. And by blocks, I mean it is removed from the queue of ready processes that we saw last week, and it is placed into the queue of blocked processes. And what is it waiting for? The process that calls the wait system call gets blocked, and it remains blocked at that state until one of its children processes terminates. Now, at the time that a process calls the wait system call, if there is already a child process that is terminated before calling the wait system call, then the wait system call will return immediately. And what about the parameter, the status parameter? Well, the status parameter, in fact, this pointer to an integer, when the wait system call returns, it will be pointing to an integer containing information about how the child process has terminated. That's the whole idea. If it is successful, it will return the process ID of the terminated child process, or -1 in case of error, and of course it will set the error global variable accordingly. Here we have an example. Now I'm not enlarging it because you have the slides on your machines, so you can enlarge it, you can zoom in on your own hardware. Now what we see on this example, so this is an example from your textbook. We can see in the main method that it receives a command line argument, which is only the sleep time, so a certain number of seconds to sleep. Okay. It calls setBuf with null, which means that it is setting the standard output file descriptor to the null buffer. So basically it is disabling buffering for the standard output. So whatever we print with printf to the standard output, it will be printed immediately with no buffering. Okay. Then we have a for loop after that. And in this for loop, it is using the number of arguments provided to it, so argc, and it will create one child process for every argument that has been provided to it. Okay, so if you have 5 command line arguments, it will create 4 children processes. So it calls fork at every iteration of this for loop. If fork returns -1, of course, that means that something went wrong with fork. But if it returns 0, that means we are in the child process. And what does the child process do? It simply prints on screen that the child process will sleep for a certain amount of seconds. The number of seconds has been provided as a command line argument. And after the sleeping is completed, it simply exits. Now be careful here, we are using the exit system call with an underscore before it. The difference between an underscored exit system call. So that's the only difference basically between them. You can read the manual page for more details. And then what does the parent process do? Since it does not enter case -1 or case 0, it goes directly to default, the parent process. It immediately breaks out of the switch. So it just basically repeats the for loop, the parent process. And at every iteration, it creates one more child process. Now, after it is out of the for loop, the parent process, it enters another for loop here below. And in this for loop, we can see that at each iteration, it is waiting. It is calling wait with a null argument. What does the null argument mean? It means that we are not interested in the value that the child process is returning. All we are interested in is waiting until the child process terminates. Now, what would happen if we didn't call wait? If we didn't call wait, the parent process would do whatever it has to do and it would just terminate. And the children processes would be left uncared for. And what happens when the parent terminates and the children are left orphans? They are adopted by the init process. Now, we will get to that in a few minutes. Now here, the parent process waits for the children processes. Now, when you call wait, does it matter which child process terminates first? No, not really. Let's say that this parent process has 3 children processes. Whichever terminates first, that will lead to the end of the wait system call. Hangisinin önce bittiğini hiçbir önemi yok. Çocuk süreçlerden hangisi önce biterse wait'ten hemen dönecek. So as soon as the child process terminates, the wait system call will end, and the parent process will continue with the if clause. And what does it do there? It basically checks whether the wait has returned -1, which means that there was an error. So basically, if the error no is set to e child, which means there are no more children. So what happens when the parent process calls wait, but it has no children processes? Well, in that case, the kernel does not leave you waiting forever. It immediately ends the wait system call by setting the error no to each child, meaning that there are no children processes to wait for. So if that happens, that means there are no more children to wait for, and the parent process can exit the for loop. And eventually, of course, the parent process just prints on screen that there are no more children to wait, and that's it. You can see on the bottom right the output of this program. Nothing fancy, just 3 children processes waiting for 7, 1, and 4 seconds correspondingly, and then it waits for the termination of those children. Pay attention that even though the children are started, they are initiated in the same order that they have been in the same order that we have given the command line argument. So the first one will sleep for 7 seconds, the second for 1 second, the third one for 4 seconds. When we call the wait system call, there is no guarantee which one will finish first. So we can see that the second one has finished first, whereas the third one has finished second, and the first one has finished third. So there is no guarantee, remember, no guarantee whatsoever in which order the processes are going to be executed as soon as the kernel gets control. Any questions about this example? Now, what about the wait PID system call? Now, the difference between wait and wait PID is basically very simple. As the wait system call does not give us any level of control, any measure of control over which child process to wait for, we have as an alternative option the wait process ID, wait PID system call, which enables us to directly tell the kernel which child process we are interested in waiting for. So we give the process ID of the child process as the first argument, and of course the integer pointer in order to collect the value with which it has terminated, and of course some options if we are interested in a particular wait, if we are interested in a particular child process to wait for. That if terminated, this system call will also block. Okay, now an important point here is that using wait, we can figure out. Please do not share your screen. Class, please don't do that. An important part here. Even though we can use wait in order to find out about the children that have terminated or not, well, because if there are any children that are still executing, wait will block. If there are no children that have terminated, if there are no children processes to wait for, wait will return immediately, setting the error no variable. However, it is not possible to be notified when a child process is stopped by a signal, or when a stopped child is resumed by the delivery of a signal. So this part is missing with the current system calls. So we can use wait in order to wait for the termination of children processes. That's fine. In order to figure out with what kind of a value they have terminated. So have they returned -1? Have they returned 0? Have they returned 1? So what is the exit status of a child process? But we cannot be notified, a process cannot be notified when a child process is stopped by a signal. Now, we can figure it out if that has taken place, but there is no direct system call that we can use to do that. But we will take a look into that in the upcoming slides. Here we have another example, also from our textbook. So we can see in this main method that the parent process is calling fork. So a child process is created. Here it is in case 0. So what does the child process do? It simply prints that the child has started with a certain process ID, and afterward it is printing what? No, it's not printing. Sorry, it is exiting with a certain exit status if the command line arguments have been provided. If not, it is simply pausing, waiting for a signal. And if it can reach this point, well, basically it will exit with a failure. And what does the parent do? The parent waits specifically for what? With a process ID of -1. Now, -1 is a special number. Basically, it means wait for all the children. Not specifically for a certain child with a certain process ID, but for all of them. We can see that we want the return value of that child process stored in this pointer, in this integer variable. And we have also given some additional options. Now, the meaning of these options, of course, for that we will check our man page. So what is, for instance, W untraced or W continued? So W continued, return if a stopped child has been resumed by delivery of the signal SIG_count, or W untraced, return if a child has stopped but not traced. Now, if you are wondering what ptrace is basically it's a tool that is used in order to set breakpoints. It is used by debuggers. Long story short, you can use wait process ID as a more powerful version of wait in order to give additional options and in order to wait for specific children instead of just any child process that terminates first. And how do you figure out the contents of status? I mean, how can you know from the value of status what has happened to the child? Now, for that purpose, there are macros that you can use that are available in the syswait header file. Two examples are, for instance, W if exited or W if signaled. Now, these are the macros that you can use in order to figure out the exact conditions under which a child process is terminated. What are these macros? We are looking at the man page of the wait system call. For instance, W if exited will either return true or false. It will return true if the child has terminated normally. And what is normal termination? Well, by calling exit or underscore exit or returning from the main function. So what if W if signaled? It returns true if the child process was terminated by a signal. So these are the macros that you can use in order to figure out that part. This is not an information given to you directly by wait. There is no value that it returns for a child process. Integer pointer that you had in the wait parameter. And you can use this macro in order to figure out if it returns true under what conditions a child process has terminated. In this particular instance, the parent returns with exit success if either the child process has terminated normally or if it has been stopped by a signal. Any questions about this example? Now we have, we have just went through the contents of this example. Now let's get to the signal handlers. Okay, now in some circumstances, we may wish to have certain cleanup steps performed before a process terminates. For this purpose, we can arrange to have a handler to catch such signals, perform the cleanup steps, and then terminate the process. Now, how should I explain this part? We had an example, right? Yes, we did have an example. Now, class, during the lecture on signals, we said that, in fact, that I gave you examples on how to handle those signals. And I specifically told you that you should have the minimum possible number of instructions, of statements inside a signal handler. Now, even though our textbook tells us that we could perform cleanup steps inside a handler, please do not be mistaken. By cleanup steps, it doesn't mean that you can, free memory, disassociate shared memory, close all your files, etc., etc. So by performing cleanup steps, the textbook here is implicitly telling us that, yes, you can, of course, perform certain cleanup steps, but you should always still keep in mind that you should keep the number of steps involved at the minimum, and especially avoid calling signal unsafe library functions, and especially system calls. So my initial recommendation to you from the past lectures is still valid. Please keep the number of statements to the minimum, and if possible, use the signal handler in order to set a flag variable, and depending on the value of the flag variable, perform the cleanup steps in your main program body, so outside of the handler. So please, I'm telling you this stuff because I do not want to see, I'm trying to avoid seeing in your homeworks huge signal handlers containing tens of instructions performing cleanup. I know that it is attractive because, I mean, that's a signal handler that is going to be executed when the signal arrives. So for instance, if a SIGINT arrives, if somebody sends a control C or whatever, but please do your best in order to avoid a high number of statements inside signal handlers. Now, what is important at this point is the following, that being said. Now, let's say that there is a parent process that wants to be notified that the child process has been terminated because of a signal. Now, if the child process, on the other hand, handles the signal, so if it has a signal handler in order to catch and handle the signal, well, that means it will catch the signal, it will handle it, it will maybe perform some cleanup steps, and then it will terminate. But in this case, the parent process will have no idea that that signal has led to the termination of this child process. So a technique that can be used is to catch the signal in the child process, use sig action in order to disestablish the handler, so remove the signal handler, and then raise the signal again after the cleanup has been performed. Now, in this case, since there is no signal handler established, when the signal arrives, it will terminate it as expected, and the parent process will have a chance to control through the macros and observe whether the child has been terminated by a signal or whether it has terminated normally. If we hadn't done this, so disestablish the and it would have terminated normally. And the parent process, even though it would check the macros, it would see that the child process is terminated normally, whereas in reality, it was terminated due to a signal. So this is a technique that you can use in order to avoid that scenario. Any questions about this? Now, the last member of the family of wait system calls is wait ID. So we have wait PID, and we have wait ID. Now, wait ID is the most sophisticated version of the wait family of system calls, and it provides us with some additional functionalities, such as, where is wait ID? Ah, here it is. Now, wait ID, as you can see, has four parameters. It can carry out some advanced stuff, such as non-blocking waits. So you can give it an option and specifically tell it by using the constant W no hang that if there are children processes of this parent process and they haven't yet terminated, instead of blocking, return immediately with an error. So this can be used as a non-blocking version of the wait system call. Because remember, normally, if there are children processes that haven't yet terminated and a parent process calls the wait system call, it will block. But if you use the W no hang option, well, in that case, if there are children processes that haven't yet terminated, the parent process, instead of blocking, it will return with an error. So it will not block the parent process. Now, wait ID is seldom used. Bu nadir kullanılan sistem çağrılarından biri arkadaşlar. Now, that being said, let's switch to the topic of orphans and zombies now. Öksüzler veya daha doğrusu yetimler ve zombiler. Now, class, as you can guess, when you have a parent process and children processes, there is no guarantee that they are going to terminate at the same time. In fact, they rarely terminate at the same time. So either the parent will terminate before the child, if it doesn't wait for them, of course, or the child will terminate after the parent. I'm sorry, either the parent will terminate before the child or the child will terminate before the parent. So this raises two questions. What are those questions? If the parent terminates before the child, so that means the child process is orphaned, what happens? Very simple. All orphaned children processes are adopted by the init process, the ancestor of all processes. So after the child process's parent terminates, it is adopted by init, and in fact, init then calls wait on those children processes. So init, in fact, will clean up after those children processes. Now, what happens to a child that terminates before its parent has had a chance to perform wait? This is a different scenario. So a child process terminates and the parent didn't have a chance to call wait. So what happens to that child process? Does it disappear from the system? No, not exactly. What happens is that when a child process terminates before the parent process has called wait, the resources allocated for that child process are, of course, returned to the system automatically. The memory, the open files are closed, and so on and so on. However, the kernel still preserves in a table the conditions under which this child has terminated it. So what was its return value, its status value? Why does the kernel do this? So that in the future, if the parent process calls wait, it will have that value, that return value to return to the parent process. Yani olur da ileride veli süreç ya benim çocuk nasıl bitti ya diye merak ederse onu ona iletsin diye. So that means if a parent process doesn't this point, the child process is basically said to be a zombie. What does it mean to be a zombie for a child process? Basically, it is called a zombie because you cannot kill it. I mean, this is a process that has already terminated, but it hasn't yet disappeared. Its resources have already been returned to the system, memory, open files, and so on and so on, but it still exists in the table of processes. If you call the ps command in order to get a list of the processes, you can see the zombie process. You can tell them apart by this status, because instead of I or SL or SL, it will have the letter Z, a capital Z in this column, in the column of stat, in the column of statistics. You will see the character Z, and Z signifies a zombie. So basically, a child process who has terminated, which has terminated, and its resources have been returned to the system, but nobody has cleaned up after it yet. So the parent process hasn't yet had the chance to call wait. Maybe it will never call wait. Who knows? Now, when, or rather if, the parent process calls wait on a zombie process, then the kernel returns the status value to the parent process, and it removes it from the table of processes, and the zombie process disappears in that case. However, if the parent process terminates without calling wait on its child that is terminated, well, in that case, the zombie child will be kept in that table. Now, not of course indefinitely. After the parent process terminates without calling wait, the zombie child, of course, will be adopted by init. Remember, when the parent process dies, all the children are adopted by init, zombie or otherwise. And then the init process, seeing that the child has already terminated and it is a zombie, it immediately calls wait on it, cleans it up, and that's it. And the system is protected from the zombie processes in that way. However, a scenario that we want to avoid absolutely is the following. A parent process creating children, the children processes terminating, the parent process not calling wait on them, and the children turn to zombies. 1 child, 2 children, 3 children, 4, 10, 100. That means this is very dangerous, because it means that these zombie processes, even though the resources are returned to the system, they still occupy rows in the table of processes of the kernel, which means we have fewer and fewer available process IDs for creating new processes. And eventually, it can fill up the entire table of processes, hence preventing the kernel from creating new processes. That is why you should always clean up after your children processes. That is a requirement always for your homeworks. So whatever children processes you create, the parent should always clean up after them by calling wait accordingly. What is the cost of a zombie process? Well, the cost is simply that they occupy a place in the table of processes. And of course, there is only a finite amount, sonlu bir miktar. There is a finite amount of such process IDs. In the case of Linux, it's usually 32 plus 1,000. In the case of FreeBSD, it's approximately 100,000, and so on. And this brings us to the topic of the SIG child signal. Any questions so far? Now, this is an interesting signal. This signal is sent automatically by the kernel to a parent process whenever one of its children processes terminates. Ne zaman bir veri sürecin, çocuk süreci bitse tamam. Now, this is important for us. This is very practical. Why is it important? Because of the following. Now, let's say that you are a responsible parent, you're a responsible parent process, and you want to clean up after your children. So what are you going to do? You have only two options. Either you're going to call wait. So if you have n children, you will call wait n times in order to clean up after all of them. But that means if the children processes haven't yet terminated, the parent process will block at wait. So it will lose a lot of valuable time waiting for its children. This is not very practical. I mean, it works, but it's not very practical because it blocks the parent process n times. Or alternatively, you will use the wait no hang flag with the wait process ID or wait ID system call, which doesn't block, and you will occasionally, the parent process will call wait PID or wait ID, checking whether a child process has terminated or not. If it has terminated, it will clean it up. If not, it will return an error, and the parent process will continue, and it will call wait PID afterwards again. But this means that you will make numerous, potentially, calls of wait PID or wait ID, which is also not very practical because it wastes CPU time. So what is the alternative? The alternative, so the third alternative, is to establish a handler for the SIG child signal, which is sent automatically from the kernel to the parent process as soon as a child process terminates. So as soon as you receive the SIG child signal, that means it is guaranteed that at least one child process has terminated. Eğer bu sinyal geliyorsa garanti en az bir tane çocuk süreç bitmiş demektir. So when you receive the signal, you handle it and you call wait or whatever you want in order to clean up after the child. Example. So here we have the main method, which establishes a handler for the SIG child signal using, of course, the SIG action system call. Here we have the handler at the top. So it calls wait. It obtains the integer that contains how the child process is terminated. It sets it into a global variable, and then it simply exits the signal handler. And then the parent process can do whatever it wants with the child exit status, use macros and so on and so on. Now, there is no waiting with blocking. There is no polling. So basically, occasionally calling the wait ID or wait process ID. It is synchronous. As soon as the child process terminates, the signal handler is invoked, and it calls wait to clean up after it. This is nice. This is a good example. Well, a good example from that regard, but a bad example in the sense that it is not checking how the system calls have terminated. Any questions about this example? Well, class, in that case, we are leaving the world of sick child and waiting behind us. And now we will take a look into another important family of system calls. Now, the fork system call, as we have seen, it creates a copy, a clone of an existing process. Same code, same open files, same variables, same stack, same heap, same global variables, initialized, not initialized, same everything. The only difference between them is that they have a different process ID. Now, if you want to, of course, convert now the child process into a different process. So basically, if you want the child process to run a different program instead of running the code of the parent process, for that, we have the exec family of system calls. Now, it will appear as a large family. So if I type man exec, you will see that it has multiple variants: exec L, exec LP, exec LE, exec CV, exec CVP, exec CVPE, and so on and so on. They all do the same thing. They all do the same thing, with the difference between them being the way that they handle their parameters. So they receive parameters in different formats. What they do is very simple. The exec family of functions replaces the current process's image with a how to reach a new program. It reads the contents of that program from the hard drive, and it simply replaces the current process with the contents of the target process. So creating a new process, remember, two stages. First, you call fork, and you create a clone of the current process. And then the child process calls exec, and it replaces its code with the code of the target program. That's the most frequent use of the exec family of system calls. Now, what are the arguments? What are the parameters of the exec family of system calls? Well, of course, you have to give it the path name, where it is going to find the target program, the command line arguments for the new program, and if you want to, you can also give it a list of, or basically an array containing additional environmental parameters. So whatever you give in these two parameters, the command line arguments and the environmental parameters, they will be passed, they will be transferred to the newly executing target program. Any questions?
May I ask a question, sir?
Of course.
Let's assume that a child process called the exec VE and its whole new process now. Does the parent process still sees it as its own child process or forgets about it?
The process ID of the child process after it calls exec doesn't change. So whatever it was, it's still that process ID, and the parent-child relationship continues. They still have a parent-child relationship. So if the parent calls wait, it will still block and wait for this child process to terminate. So exec doesn't change that. This is not evec, this is exec. This is a typo here. Sorry for that. So exec, it simply replaces the code and the basically and the memory contents of the child process with new contents. That's all. But it doesn't disrupt, it doesn't change the relationship between the parent and the child. Yes, okay. Now what is important is that if exec is successful, so if it successfully changes the contents of the child process, that means it shouldn't return. That means a successful exec must not return because the code has changed now. We are executing a different program from the beginning. That is why you never need to check whether exec VE has returned something or not. So it will always be -1. If you see that it actually returns something, well, that means already that something has gone wrong. Exec is not supposed to return. It is not supposed to return. That is why it only returns -1. And of course, there are several sources of errors. For example, if it cannot find the binary program to execute, and so on and so on. Here we have an example. So this program is receiving, well, what is the program doing? Well, it has a certain array containing two environmental variables, greet and buy. It has certain command line arguments such as hello world, goodbye, etc. And argv0, of course, as you know, it must contain the name of the program to be executed. argv0. argv1, 2 are command line arguments, and of course it is null terminated. And it is simply calling execve by giving it the name of the program to execute, the command line argument array, and of course an array containing environmental variables. In this case, only 2. The environmental variables must be in this format. So variable equals value. That's how it works. Here, for instance, we have a program, a target program, which very simply prints on screen its command line arguments and its environmental variables. So if you execute the previous program, giving it this program as an argument, so right target program, the one that you see just above it. So it prints on screen the command line arguments, the name of the program at position 0, the 2 command line arguments at position 1 and 2, and 2 environmental variables, greet and bye. Any questions about exec? Now, in this library of functions, in this family of exec functions, they are not library functions, they are not C library functions. These are system calls. Be careful. Now, what they do is the difference between them is basically provided by the last 2 characters of the name of the system call, LE, LP, VP, and so on. If you see V, that means it is expecting an array of arguments. If you see L in the name, that means it is expecting a list of arguments. The behavior of the system call is exactly the same across all of them, across all 5 of them. The only thing that changes is the way in which you give, for instance, the path name. You can even give it, you can either give it a full path name, or you can just give it the file name and then tell it to look for the binary program in the path of the system, depending on whether you use exec v or exec vp. So depending on whether it has the letter P in its name or not. If it has the P, it will also look into the path. Otherwise, it will go directly to the path name that we have given it. V and L determines whether the parameters are given as a vector or an array. Sorry, as an array or as a list. And the if it has the E character at the end, basically it means that you are going to give it explicitly an array containing the environmental variables. Or if it is empty, it will simply use the environmental variables available from the parent process. But besides that, all 5 of them, they do exactly the same thing. So the only thing that changes is basically the way in which you give the parameters. Now let's get to the complicated part. What happens to the signals when you call exec? So what happens when, for instance, you have a child process, which we had some signal handlers. It gets set certain signals to default disposition, some of them to ignore, and so on. And then you call exec. Now, the rule is very simple. When you call exec, since the signal handlers were part of the code of the previous form of the process, of the previous contents of the process before calling exec, all of them disappear. So all of the signal handlers are cancelled in the child process, and the signals that they were associated with, they are set to the default disposition. So if you had, for instance, a signal handler for sigint, it is set to the default behavior. All the other signals, so all the other ones, so the ones for which you didn't have a signal handler, they are left unchanged. So whatever was the disposition for them, it is left unchanged. So in general, the practice is, if you intend to call exec in a process, do not establish signal handlers because they are going to be overwritten anyway. Here we have such an example of calling fork and exec. We have the main method at the bottom. It calls the spawn method. This spawn method is defined here in this program, so it is not a system call or a library function. It simply contains the ls program to be executed, the ls command, and an argument list. And what does spawn do? It calls first fork in order to create a clone of this process. The parent process returns immediately, and the child process calls execvp using the arguments provided to spawn in order to replace the child process with the contents of the target program. And if it reaches this point after execvp, that means something went wrong in execvp and it aborts the program. Normally, after calling execvp, this content, this code doesn't exist anymore. It is overwritten with the contents of the ls command. Any questions about this example? Now, class, we will take a look. Although the name is a bit misleading, the system function is a function available in the C library, and I highly recommend that you don't use it. Genelde insanın başına iş açıyor. Kullanmayın. Şunu arkadaşlar, kullanmanızı tavsiye etmiyorum. Ödevlerde hiçten kullanmayın. Do not use it in your homeworks. Do not use it while you're a student, while you're taking this course. After you have graduated, you can do whatever you want. Now, why? Why don't I want you to use the system function? What is the problem with it? But before the problem, what is it exactly doing? Now, the system function is there in order to make our lives easier, but in general, it makes it more complicated. Now, the system function, it simply receives a command as a parameter. So ls, ps, army, mv, whatever you want, a command. And it creates two processes in order to execute it. First, it creates a shell process, and the shell process creates the process of the target command. It executes the command, and it returns the status with which the command has terminated. So it is there in order to make it easier for us to go through the fork execvp procedure. Now, let's look at the details. The advantages, it's very simple. Instead of dealing with fork and exec and wait and so on, you simply call system, and that is all. You do not have to worry about signal handling and error handling and so on. It is completely taken care of by the system function. And not only that, but it also helps us with shell processing. So if you use any shell variables, if you have any redirections, substitutions, and so on, they are all performed by the system function. So it makes it very easy to execute a shell and execute some commands. The downside, the disadvantage of the system function is, first of all, inefficiency. There are two downsides. The first is inefficiency because it creates two processes, one for the shell, and then the shell additionally creates the target process. And of course, since it creates two processes, this takes a lot of time, relatively speaking, because remember, fork and exec are expensive system calls. And the second downside is that is security. Because if the shell that is present, that is installed on the system where this program is executing, if that shell has any security flaws, that means your program, which is using the system function, which will use in turn the shell of that system, of that operating system, will also suffer from the same security flaw. Eğer kabukta varsa arkadaşlar bir güvenlik problemi, siz de o kabuğu kullandığınız için kendi programınızda komutları çalıştırmak için haliyle sizin programınızda tabii ki bu durumda o güvenlik probleminden muzdarip oluyor. Dolayısıyla hani çok mükemmel bir program yazmışsınızdır ama sistem kullandığınız için o çalışan sistemdeki güvenlik probleminden sizin programınızdan nasibini alacak. Here we have an example. So in the main program, we have a character array containing the command to be executed. We get the command from the standard input So we are asking the user to type it in to the command line. We use system in order to execute it. We use this return value in order to check how it has returned. So we can use some bit arithmetic in order to figure out what exactly happened. And depending on the value that has been returned, we can figure out what went wrong. Did the system function fail? Did the shell that we tried to create fail? Or did the process that we want to create through the shell fail in any way? So we can check the returned values in order to figure out what exactly went wrong. And we do not have to worry about error handling or signal handling or anything. So it is very simple. You just give the command to the system function, and then you just obtain the return values, and that's it. Nothing more than that. But it will be a bit slower than calling fork plus exec, since it is creating two processes instead of here we have an example. So we execute the previous command. We give it the command who am I. It gives you the name of the current user. So you can give it pipes. So ls, its output given as input to grep, and so on. So no problems. It is executing without any issues. So it is quite powerful, in fact. Very simple, powerful, but inefficient, especially if you're developing a real-time system. You should definitely the system library function in that case, and especially if you are very sensitive about security issues. Now, if we wanted to implement system, or basically if we wanted to just simply have a program that receives the information of another program in order to instantiate it, in order to execute it, now we should be able to just achieve it by simply calling exec, one of the exec functions, execl, execvp, or any of them. Simply give it the name of the program to execute, or basically the path name, and then the command line arguments. So what are the command line arguments? Well, the command line arguments is execute the shell, so sh, the command line arguments with the C, and here is the command to execute, so bin sh. And now terminated list of arguments. So what is it going to do? It will create a shell, and we are telling the shell, well, basically it will simply just create a shell. That's it. And that shell will execute in its turn the command that we wanted to execute. So we will create two processes, eventually, the shell, and the shell in its turn will create the process executing the target command. Here we can see it in play. So this is our version of the system library function. It is first calling fork in order to make a copy of the parent process. The parent process creates an instance of the shell, bir kabuk programının süreç halini oluşturuyor, which receives as argument the target command to be executed. Now, if execl fails, that means it will reach this point. If it can reach this row, this statement, that means exec failed. So it returns 127 to let us know that exec failed. We could not create the shell. Otherwise, the parent simply, in that case, waits for the child. It knows the process ID of the child since it was obtained by fork, and it waits for it. And whatever it has been returned as the return status, it is stored in the status variable. If wait fails, it returns -1, something went wrong. Otherwise, it returns the status variable corresponding to the target process. So as you can see, the system function is not really that complicated. So if we do it on our own, we will very simply avoid creating the shell process. So instead of two processes, we will simply directly create just a single process. Any questions about this example? Pay attention at this point how we have used the wait PID instead of wait. If we had used wait in order to wait for the child, that would be a bit dangerous because this parent process might have more than one children processes, in which case we are here interested in waiting for the result of this command, but instead some other child process might terminate first. So in that case, we will have the wrong return value. By using wait process ID, wait PID, we are specifically waiting for the termination of this child process. Now, what happens with signals inside the system library function? Now, things get a bit complicated. Things get a bit complicated inside this library function. That is why I highly recommend basically avoiding it. But anyhow, now, how do you treat the signals? How do you treat the signals in this case? First of all, let's look at sig child. Now, this signal is a signal that is sent by the kernel to the parent process whenever a child process is terminated. Okay. For which it has established a handler for the sig child signal, and it is performing its own wait. Now, what is the problem? The problem is that when a sig child signal is generated by the termination of a child that has been created by the system function, it is possible that the signal handler of the main program will be invoked, and it will collect the child's status before the system function had a chance to call wait process ID. So basically, the parent process has executed all of this code, and it is just about to call wait PID, but before calling it, the child process terminates because we never know which one will run first. The sig child signal is sent to the parent. The handler is invoked where it calls wait. The child is cleaned up, and then the control returns to the parent process. And then the parent process calls wait PID. But since the child process has already terminated and it has been cleaned up, here it will be blocked, waiting for that child. Or it will receive an error specifically saying that this child has been already cleaned up and it has lost the chance to obtain the return status of that child. So what do we do in that case? Well, the idea is very simple. System must block the delivery of the sig child signal while it is executing. This way, it is guaranteed that the system function will catch. It will get a chance to wait for the child before the signal is handled by a potential handler. But not only that, but we have to also consider other signals that it might be generated by the terminal, such as Control C and so on and so on. So we have to pay attention to it, and especially SIGINT and SIGQUIT, they should be ignored in the calling process while the command is being executed. So what is the proper way of implementing system in this case? Well, if you really want to implement it in the proper way, well, in that case, you have to use your signal masks in order to definitely block sig child, and not only that, but also ignore SIGINT and SIGQUIT while that command is being executed. After you have called wait, after you are done cleaning up your child, well, in that case, after that, you are free to unblock sig child and of course restore the default dispositions of SIGINT and SIGQUIT instead of ignoring them. So as you can see, if you want to do it properly, there is a lot of handling for the signals. Long story short, avoid using the system library function. And if you want to properly handle the signals in this case by implementing your own version, make sure that you block the sig child signal while executing the command. Why? Because in case you have a signal handler handling the sig child signal, you might not get a chance to obtain the return value of the child process. That's the whole idea. It's a very subtle risk, but it is a risk all the same. Or alternatively, instead of doing all this stuff, simply do not use the system library function. Now, if we go beyond the parent-child relationship, you will see that there are some additional concepts, such as a session or a group. Processes not only have a process ID, they also have a group ID, they have a controlling terminal, and they have a session ID. Now, we rarely use these concepts, but still, it is important to know about them. Now, imagine that a user has created several processes, and some of them have been set to execute behind the scenes. Now, when a user logs out of a system, so when you close your session, but you do not shut down your machine, the kernel needs to terminate all the processes that the user had running. And so it needs to identify them. Keep executing even after you log out. So it needs to make the distinction between the processes tied to the session and the processes that are independent of this session, the processes that need to remain active after the user has logged out. So that's why it has a session ID in order to characterize those processes. And using the session ID, the kernel can collectively terminate them as soon as the user logs out. Another important concept is, of course, the group ID. In collective grouped commands, such as this one, where the output of one command becomes the input of the next one, and so on, which basically is known as a job, the kernel needs to be able to control, basically stop, suspend, and continue these collections of commands. So it needs to know that these commands are related with each other. In this case, it is using the group ID in order to make sure that all of these commands, these three commands, ls, grep, and more in this case, belong to the same group so that it can stop and suspend them collectively. So if you look at it closer, you will see that basically a process ID is accompanied, process ID'nin yanı sıra, process ID is accompanied by a group ID and also a session ID. A controlling terminal basically is the terminal that is tied to a session and from which the processes can get their input. Now, the terminal to which a session is related is called the controlling terminal or controlling TTY of the session. And a terminal can be the controlling terminal for only one session at a time. Now, this is an important concept, the controlling terminal, because it is related to daemons. Now, daemons are not different. They are just regular processes, just like all the others. Everything that we have talked about so far is also true for daemons. But daemons, since they have a different name, they are also a bit different from regular processes. How are they different exactly? Now, daemons are processes that usually have these characteristics. They are processes that are supposed to run for a long time. Usually, they start when the system, the operating system boots up. Yani bilgisayarınızı başlattığınızda, işletim sistemi başlarken başlayan süreçler bunlar. Also, they run in the background with no controlling terminal. There is no terminal where you can type something and send it as input to a daemon. They do not generate job control or termination related signals. And very usually, they have names ending with the letter D. So let's look at the processes active right here. So we can see, let's look at the processes. So these are the processes that started very early. We can see Ksoft IRQD, it ends with a D, that's a daemon. Another one. Compact, K compact D, another daemon. KSMD, K huge page D, K integrity D, K block D. These are all daemons, daemon processes. So that means they have no associated terminal. they were created, they have very small process IDs, meaning that they were created, they were instantiated when the system was booting up. And even after a logout, they will continue to be running in the background. So server processes, database servers, web servers, they are usually daemon processes that run in the background. So now the question is, how can you convert a process to a daemon process? What are the steps to be taken when you want to convert a process to a daemon process? Yani arka planda çalışan, hiçbir terminali falan filan olmayan, sakin, sessiz arka tarafta çalışıyor. Sen bilgisayarının oturumunu kapatsan da açsan da başkaları da girse o arkadaş işini yapmaya devam ediyor. How do you accomplish that? Now, to become a daemon, there are certain steps that you need to take. Now, first of course, the parent process must call fork in order to create a clone of the parent. After which the parent exits. Now we have to disassociate ourselves from the controlling terminal. In order to do that, you have to call set session ID twice. First, the child process calls set session ID. This means it will start a new session and it will free itself from any association with the controlling terminal. Why do we want to do this? Because if somebody sends a kill signal from that terminal, it will kill the daemon. We do not want the daemon to be killed accidentally. If the daemon later opens up a terminal device, then we also need to take steps to ensure that the device does not become the controlling terminal, which is why we will call it second set session ID. We will see it in the example. So first, you call fork. The parent exits, the child continues, so that the shell will return to its prompt. 2, you call set session ID to create a new session and free yourself from the previous controlling terminal. 2, you call one more session ID in order to make sure that you do not accidentally obtain a controlling terminal after that. 4, you clear the process umask to ensure that when the daemon creates files and directories, they will have the requested permissions. 5, you change the process's current working directory and you set it to the root directory. 6, you close all open file descriptors that they have been inherited from the parent. And 7, after having closed file descriptors 0, 1, and 2, you explicitly open dev null, the null device, and using dup2, you duplicate it so that all 0, 1, and 2 refer to the null device. So this way, all the input, output, etc., they all go to null. They all disappear. And plus, neither the daemon nor its children will write to the terminal when running or detaching from it. So you're making it certain in this case that nobody will ever have a controlling terminal. So it will be impossible to basically end these daemons by sending them signals through any terminal. Let's look at an example. So here we have the become daemon pre-processing steps in order to prevent double inclusion. We have some bitmask values for the flags to be given to the become daemon function. So these are the flags that are received by it. Okay, so this is our prototype. Now, why are we so adamant? Neden çok ısrar ediyoruz? Why are we so adamant on closing the 0, 1, and 2 files? That is because so that the daemon can detach successfully from the controlling terminal it was started from, and also so that the daemon or its child processes, children processes, won't write to the controlling terminal when it is running. Because if they attempt to write anything to it, it will automatically become a controlling terminal. So if you look at the become daemon function, we see that it first calls fork to create a clone of the parent process. The parent process immediately exits. Oh, sorry. The parent process terminates successfully, so the shell prompt is back. And the child process gets out of the switch. It first calls set session ID to become the leader of the new session and disassociate itself from the controlling terminal. It calls one more fork in order to make sure that we are not the session leader. So this is guaranteeing that the controlling terminal will not be acquired by accident. It clears up the UMask so that the inherited mask will be cancelled and we will set up our own mask with the permissions that we want. It changes the current working directory to the root directory. It is closing all open files inherited by the parent process. And then it is explicitly opening the dev null, the null device, and it is setting a steady in, a steady out, and a steady error, the standard error output and input, to point all of them to the null device. So that even if this daemon or its children processes ever attempt to write, to print anything to 0, 1, and 2, it will go to the null device and it will never have a controlling terminal. This part is not really that important. The SIG term, well, of course, I mean, if somebody sends the SIG term directly to a certain process ID, they are supposed to handle it if you want them, if you want those daemons to handle them. And the tradition, yani gelenek olarak, the tradition in the case of the SIG hub signal, in the case of daemons, is that it is used in order to trigger the daemon to reinitialize itself. So basically, it is used in order to reset the daemon. So read again your configuration files and restart yourself. That is just a tradition to keep in mind. So in case you ever have to write a daemon, keep in mind that these traditions are in place. Any questions?